Hi class, it's Mr. Endicott here, and today in chemistry we're going to talk about a concept called enthalpy, also denoted as delta H. So enthalpy is described as the amount of heat absorbed or released in a chemical system during a process at constant pressure. And the equation for enthalpy is enthalpy of the system, H, is equal to the internal energy of the system, U, plus the product of the pressure and volume of the systems. Now, internal energy is just simply your total sum of your kinetic and potential energies. And the product of the pressure and volume is actually the work being done by the system onto the surroundings. Now, H by itself is not what most scientists use, and the reason we don't use just H is because it's not actually possible to measure the total enthalpy or heat content of a substance. There's just way too much stuff going on. But what we can do is we can measure the changes in enthalpy during a chemical reaction. So if we look at this equation here, and we make a whole bunch of assumptions, such as, the pressure is going to be constant and the only work allowed is a change in volume. And we, do several different rearrangements to this equation. We can actually come up with this new equation, which is that the change in enthalpy is equal to the heat of the system at constant pressure. And this is an amazing equation because it's super simple. But even beyond that, it tells us that when you have a change in enthalpy or a change in energy for a system, or in other words, when the reactants are changing to the products, these will be equal to the heat, and we define it as Q here, content of the system, provided it's at a constant pressure. And delta H itself, the change in enthalpy, is equal to the enthalpy final minus enthalpy initial. And notice that these I don't have delta signs on here because these are going to be experimentally determined values. So they're exact. But the difference between them will tell us what the change in enthalpy is. This is also the same as saying that the enthalpy of the products, take away the enthalpy of the reactants, will give us the total change in enthalpy. Now, the SI unit for energy is the joules, and specifically when we're talking about chemical systems, we're going to be talking about energy in terms of kilojoules. So how do chemists communicate the changes in enthalpy? How do we show what we've done? Well, there's some different ways, and most of the information about energy changes, like we said earlier, are experimentally determined from the process of calorimetry. Now, these methods yield enthalpies, and we can look at it in four different ways. We can say that it's the enthalpy of the reaction, or we can state that the enthalpy change for a balanced equation is within the equation itself, or we could include the energy value outside of the equation, or we could draw potential energy diagrams. What you see in front of you is the enthalpy of reaction. Now, this is also called the heat of reaction. They mean the same thing. And this delta sign simply just means the change of. H is still our old friend enthalpy. We don't want to let this fella feel like he's left out. This is for any type of reaction here, and it's going to be conducted at standard state conditions. And what are standard state conditions? 25 degrees Celsius, folks, also known as 298 Kelvin. Also, if we're talking about gases, we're really talking about 1 atmosphere of pressure, or in solutions, we're talking about 1 molar. So let's have a look and see how we write enthalpy changes beside a chemical equation here. So let's just go to the next page here. So if this is an enthalpy change, first thing we have to make sure the equation is balanced. Once it's balanced, we can displace the enthalpy side outside of the equation to the right, indicating the value, whether it's positive or negative. In this particular case, it's negative. It's an exothermic reaction where we have carbon monoxide plus 2 moles of hydrogen are producing methanol. Now, if you want to include the energy sign within the chemical equation, this is how you would do it. You would take the energy sign, be it positive or negative, and if it's an endothermic reaction, it's positive, you would put that on the reactant side. If it's a negative value, That means it's exothermic, and you would put that on the product side. And notice that even though one is positive and one is negative, we still indicate the energies as absolute values. In other words, they're going to be positive values. Just one's on the reactant side, one's on the product side. So here we have water plus 285.8 kilojoules of energy, which produces hydrogen plus 1/2 moles of oxygen. So the water needed this much energy in order to make the reaction move forward. Now this one says that if I have magnesium and I combine that with 1/2 mole of oxygen, the reaction will go by itself without a net input of energy and will produce magnesium oxide. And it will give off 601.6 kilojoules of energy from the system into the surroundings. Okay, so the final way to communicate, or that we can show changes in enthalpy, is to look at potential energy diagrams. But before I get to that, I want to talk to you about the first law of thermodynamics and what happens during a chemical reaction. So we know that the first law of thermodynamics states that the total energy of the universe cannot be created nor destroyed. It can only transform. So it means that the energy of the universe is conserved. So whenever you have a chemical reaction, whenever a reaction occurs, there's always going to be this change in energy. And this energy comes from stored potential energies in the chemical bonds that hold the atoms together in order to form the molecules. We call that intramolecular forces. There's also going to be forces and energy between the molecules called intermolecular forces. Now, during a chemical reaction itself, the bonds on the reactants are going to get broken, and these bonds are going to become rearranged to produce new products. So it's going to form a new substance. So in order to break the reactant bonds, there has to be a net input of energy. So energy has to be absorbed by the reactants to split them. And then new bonds are going to form in the products, and a certain amount of energy is going to be released. Now, depending upon the net difference or the energy change between the reactants needing to absorb energy from the surroundings in order to break the bonds, as well as the products creating new bonds and releasing energy, we can say that the reaction is going to be endothermic positive or exothermic negative. But we have to understand that the total amount of energy within the system is conserved. So these two formulas are synonymous. It just simply says that the change in energy of the universe is equal to the change in energy of the system plus the change in energy of the surroundings. Well, that's really the same thing as saying that the change in internal energy of the universe is equal to the change in internal energy of the system plus the change in internal energy of the surroundings. And what does this mean? Well, if we think of this as the total universe, okay, then if this is the universe here, then this in here will be the surroundings, and this will be the system. So this is going to be our chemical system happening here, and it's either going to absorb energy from the surroundings, or it's going to liberate and give off energy to the surroundings. Even though that we're conserving energy, the energy can clearly be transferred from one part of the universe to another. So let's have a look at endothermic reactions. What are endothermic reactions? Well, the reactions that require more energy to break the bonds of the reactants than is going to be released by producing new bonds during the formation of products. Now, there's different ways to look at this. If this is, again, this is our surroundings, and this is our system, and this is our total universe here. In an endothermic reaction, what's actually occurring is enthalpy, or heat energy, is being put into the system. So the amount of energy within this system is increasing. So we say delta H is positive. If we look at this in terms of a potential energy diagram over here, you can see that your potential energy of the reactants is much lower than the potential energy of the products. So in order to make this reaction proceed, we have to have a net input of energy by the reactants from the surroundings. So in other words, if we take the difference between the products and the reactants, so I'm just going to do it right here just like this. This is actually your enthalpy final, and this is your enthalpy initial, and you know that Your change in enthalpy is going to be the difference between the products and the reactants. This is going to be a positive value. In other words, Q, the amount of heat, is going to be greater than 0. So it tells us that not only do we need to have a net input of energy here, but that the reactants are starting off at a lower potential energy than the products. Now think of this like a large boulder sitting down here. This is not naturally going to just roll up this hill. You have to have a net input of energy to make this move forward, to make this go uphill and, and do work. So in chemical reactions, it's the same thing. If you have a lower potential energy of your reactants than you do of products, the only way you're going to get a reaction to proceed is to have a net input of energy. And there's a couple examples. So down here we have water and carbon, and we have a net input of energy. So we have 132 kilojoules of energy put into the reactants, and those bonds will be broken and they're going to reform new products and new substances. And in this particular case, it's going to be carbon dioxide and water. Now notice that we could have that same reaction, and I can show the enthalpy change on outside the equation to the right here. Now, in terms of exothermic reactions, in this particular case, more energy is going to be released during the bond formation of the products than will be absorbed by the reactants to break the bonds. In other words, Q, heat, will be less than 0. It's going to take on a negative value. So again, if we think of our old trusted friend here, the surroundings and system here, this is going to be the surroundings, and this will be my system. What's going to happen here is your delta H is going to take on a negative value because it's losing or liberating heat energy into the surroundings. Again, keep in mind the total energy here is conserved between the surroundings and the system. So another way to think about this is that your reactants are going to start at a higher potential energy in this potential energy diagram than will the products end up at. So it's going to decrease in energy. Again, if you think of this in terms of a large boulder, if I let that large boulder go, it's going to follow the natural inclination of this slope, and it's going to roll down this hill, and that higher potential energy is going to turn into kinetic energy, and it's going to do a whole bunch of work as it's going down the hill, and maybe smash something when it gets down here. So it's going to be at a much lower energy by the time it gets down to this level here. So the reactants are at a higher potential energy than are the products. Now a couple of examples here. We say we have copper and chlorine and we mix them together, and it spontaneously is going to produce carbon 2 chloride, and it's going to give off 220.1 kilojoules of energy into the surroundings. Now the same reaction could be denoted to the right as we did before, with the delta H of reaction at standard state conditions equaling negative 220.1 kilojoules. Don't forget the sign is very important here.